Here's sample test 2, problem number 7. A particle mass 6.7 times 10 to the minus 27 kilograms, charge 3.2 times 10 to the minus 19 coulombs, moves along the positive x-axis with a speed of 4.8 times 10 to the 5 meters per second. It enters a region of uniform electric field parallel to its motion and comes to rest after moving 2 meters into the field. What is the magnitude of the electric field, and what change in potential did the particle go through? Well, if we're looking at this particle of 6.7 times 10 to the minus 27 kilograms, that is 4 times the mass of a proton, which is 1.67 times 10 to the minus 27 kilograms. So we're looking at a unique particle that really has 4 unit masses, and its charge is twice that of the positive proton. So we're looking at a particle that kind of looks something like this, where it's got 2 positive charges, like a proton's, and then 2 neutral charges. So it's really 2 protons and 2 neutrons. There's a name for this particle, and that is an alpha particle. So you don't have to know this, but extra information. And it's going to move 2 meters before it stops, which must mean, since it's a positive charged particle, that the electric field must be working against it. So the electric field is going, as I'm drawing it here, in the negative x direction, as this is moving in the positive x direction. Sounds good. And starting off with initial kinetic energy, ending up with no kinetic energy. So the initial kinetic energy of this particle is 1/2 mass times its initial velocity squared, and that's going to be 1/2 times 6.7 times 10 to the minus 27 times its initial velocity 4.8 times 10 to the 5 meters per second, all that squared. And this is going to be 7.718 times 10 to the minus 16 joules. Final kinetic energy will be 0 because it came to rest. So our change in kinetic energy, which is our final kinetic energy minus our initial kinetic energy, is going to be a negative 7.718 times 10 to the minus 16 joules. Sounds good. If we're using energy considerations, we know that for this kind of field, the change in potential energy plus the change in kinetic energy is equal to our change in energy, which actually is 0. So our change in potential energy is going to equal the negative of the change in kinetic energy, and hence it's going to be a positive 7.718 times 10 to the minus 16 joules. Well, we know that the change in potential energy is equal to the charge times the change in potential. So the change in potential is going to equal the change in potential energy divided by the charge. That's going to be equal to 7.718 times 10 to the minus 16 joules divided by the charge, which is 3.2 times 10 to the minus 19 coulombs. And this is equal to a positive 2,412 volts. Makes sense. This particle is going up in potential because it's a positive charge and it's gaining potential energy, losing kinetic energy. It's going up in potential. Sounds good. Well, we know that the change in potential is equal to negative field times distance for a constant electric field. So the electric field is going to equal the negative change in potential divided by the distance. in this case. That is going to be equal to a negative 2,412 volts divided by 2 meters, which would be a negative 1,206 volts per meter. We just want the magnitude of this field. So that's just going to be 1,206 volts per meter. So this is part A and part B. We did part B first and then part A. There's other ways to do this problem, but this is the easiest way using energy considerations. For instance, another way you could do it is to calculate the acceleration as this particle is going to rest in a constant electric field. So the acceleration will be constant. Once you get that acceleration, you can figure out the force of the electric field and then solve for the magnitude of the electric field that way, and then find the potential. But I think this method that I've just shown you is indeed the easiest and fastest way if you can understand how to do this.